Okay, everyone, it looks like it's about 7 o'clock, so I'm going to kick things off. Today we're going to be talking about shellcoding, which is a really interesting way of injecting your own code into a running process so that you can make it do things that you wouldn't be able to do with a more traditional basic like stack smashing attack like we talked about last week. So a quick agenda, we want to review some things that we talked about on Monday. So that'll basically entail like the basics of stack frames, how return addresses work, things of that nature. And then we want to kind of reiterate that information that we discussed on Monday about basic stack smashing. So if you made it on Monday, if you were there for that talk, that's great. If you weren't there, that's totally fine as well. There are a lot of different ways that people learn about this. I think that it's even discussed very briefly in certain classes here at RPI. I know, for example, we often have a guest lecture for operating systems where we talk about the basics of stack smashing. But either way, we're going to quickly go over that again, make sure everyone's on the same page. And then another thing that we kind of skimmed over last week, or on Monday I guess I should say, was the process of actually sending these raw bytes, which is really important for exploitation. And then once we kind of have everyone up to date on the review of Monday's talk, I want to jump in and talk about shellcoding and some of the constraints that we have to deal with when we're writing shellcode. So with that out of the way, without further ado here, I want to hop into a quick rundown of how stack frames work. I know we've talked about this probably 4 or 5 different times now, but it is actually really, really important for the stuff that we're talking about right now. So because we're working with a 32-bit system, we have 2 registers that kind of define a stack frame. And those are going to be the base pointer, EBP, and the stack pointer, ESP. And the base pointer is going to point to the base, or the bottom of the stack point, or of the stack frame, and ESP, the stack pointer, is going to point to the top. And so that's going to point to, for example, where data will be pushed to or where data will be popped off of. And so within that stack frame, we hold a lot of really useful information. So we hold local variables. So if you have a function that has like an integer foo, for example, then you're going to have that variable will be within the stack frame for that function. It also points to the previous stack frame so that it kind of saves the base pointer. It takes the previous base pointer from whatever function called this one, and it throws that onto the stack above all the local variables. And likewise, it kind of does the same thing for the return address. And that saved base pointer and that saved return address are basically just a way that we can ensure that we jump back to the right point in the code and also the right point in the stack when we call a function we return. So for example here, we just have a little function called foo. We have a long, which is OX1337. That's going to be in this variable x here. And then we also have this character buffer. And when we call gets on that, that's going to get some input into that character buffer. And we've kind of drawn out what the stack frame will look like here. So we have the return address up at the very top. That's going to point to some other point in our code. We're going to have some previous base pointer, and that's going to point to some other variable on the stack, some other location on the stack. And then we're going to have this local variable for x, that OX1337. And then we're also going to have that string variable here. So we're going to have, in this case, 8 bytes. We have 4 A's and then another 3 followed by a null terminator. So a total of 8 bytes, which matches up with the buffer length there. So on Monday, we started talking about, okay, what happens if we start abusing these? What can we do if we have something like a call to gets here where we can put in an arbitrary amount of data? So we know this character buffer can hold 8 bytes, but what happens if we start putting in more than 8 bytes? And so basically what's going to happen then is we're going to be able to overflow into other stack data. So right here, we've taken, instead of having, 4 A's and then another 3 followed by a null terminator. This is actually a typo here. I should have removed that null terminator from the middle of the string. Because after those 8 bytes, we just keep going. We put another 4 in after that. Now instead of x being OX1337, x is going to be OX41414141. And that's basically just going to be the hex equivalent of 4 more A's on top of that. So we can overwrite local variables on the stack, but we can also overwrite other special data. So when I say special data, I'm referring mainly to that saved base pointer and that saved return address. So we can see if we just keep putting more A's in, now instead of having, 8 A's filling up the string buffer, or instead of just overwriting that x variable, now we've overwritten the return address. And so when the function goes to return, it's going to look at this section of memory and it's going to try to jump to that and start executing the code there. And so we talked about how we can kind of abuse that knowledge of how the stack works, and we can kind of put in our own special value there. So instead of just throwing more A's in, instead of just making that return address 41414141, we can put in a special return address which lines up with some other function in the code that we want to jump to. So it's pretty common in a lot of beginner CTFs to have like a win function like this, where you just need to find some way to abuse a return address or a function pointer or something like that, and then just jump right to that win function. However, there is kind of a trick to that, and we need to know how we can send an address here. We need to know how we can send those raw bytes, because when we send A, we know that's really easy. We can just type that out on our keyboard, but when we want to send, for example, OX like 401337, those don't line up with letters on our keyboard, and that's going to be a lot more difficult to send. We can't just do like print OX 401337, because that's just going to give us a number. And so we talked about a couple of ways to do this. One of the reasons why a lot of people in the security field really like Python 2 is because it handles these raw bytes really, really well. So if we want to just send that string, we just escape it with these \x characters, and then that'll just print out the raw bytes right to the screen. We can pipe that into another program. We can still kind of do the same thing in Python 3, but it's a lot more annoying. So instead of just being that one clean call to print, we have to import a library, and then we have to write to the standard out buffer, and it's really garbage. It's hard to do in a like one line like command line call that you can then pipe into another function, or into another program, I guess I should say. And one thing that we talked about earlier in the semester, we kind of alluded to and we hinted to, was a resource called Pwntools. I don't think we talked about it so much on Monday, because we wanted to give the very, very basic introduction to how you might be able to do this, and we didn't want to get too into the weeds with other tools. But Pwntools is actually a really amazing set of tools. It's this really incredibly powerful toolbox that's designed for people that are working on CTFs or doing any kind of binary exploitation like this. So we can see if we wanted to do the same exact thing in Pwntools, instead of having to print out some string and then pipe it into another program that we're running, we can just start up that process, and then we can send that process information very, very easily. And so there's a million different cool tricks that Pwntools can do, but for right now, for the purposes of this talk, we're going to be focusing on these 4. So there's that process call, that constructor, and that's going to create that process. It's going to start that process up. It's going to launch that binary, and then you have P32 and P64, which effectively pack that input into a 32 or 64-bit string. And so you can see in the previous slides here, we had to worry about endianness. We had to flip these strings around. And if you've taken comporg or a similar class, I'm sure that endianness conversion is the bane of your existence. I'm sure you're all too familiar with that. But P32 and P64 in Pwntools do all of that automatically, which is really amazing. And so that makes our life as a security researcher so much easier. And then lastly, the final function that we kind of want to be thinking about is that process.interactive function. And that will connect the standard in and standard out from your terminal to this process. So that will allow you to interact with it just with a keyboard, essentially. It'll allow you to interact with it as if you're running it natively without any kind of Pwntools in the mix. So that was a really, really basic, quick overview of all of the things that we talked about on Monday. And with that out of the way, I want to get into some of the meat of what we're going to be doing today, which is code injection, and specifically shell coding as a means of code injection. So we kind of alluded to the idea of a win function earlier today. We alluded to the idea of this function that you just need to figure out some way to call it, and once you call it, that's it, you're done, you get that flag. And so we see a bunch of these different win functions where it'll compare like a password or like a user provided string to a fixed password, and then it'll cat that flag out. We can see like in some of these other ones we have a void get shell, where literally you just call this function and it'll execute system bin.sh, which will just give us an interactive shell essentially on the target machine. And these are incredibly useful. These are a great way to get started. But unfortunately, in the real world, we don't see those so much. And so if we want to be able to execute any arbitrary code, that's much more difficult because there isn't just a random function already in the binary that can do everything that we possibly want. And so I wanted to show you guys this video really quick. This is a really famous example of code injection. It's actually in Super Mario World. So this is a really famous video game as well. And I believe this was a speedrunner who discovered this. And if we hop in, let's just jump ahead a little bit. We can see this guy is doing all of these weird things. He's triggering these strange bugs. He's jumping back and forth. You know, not playing this game like a normal person would be playing it. And this seems like very erratic and random behavior, but in reality, it's incredibly calculated. It's incredibly planned out. And so we can be jumping back and forth here. We can be seeing like they're continuing to run around to act crazy and erratic, even though this is incredibly precise and well-timed. And then if we skip ahead a little bit, we can see here they've finally moved around in such a way. They've manipulated memory while they were moving around in this seemingly random and erratic fashion in such a way that they actually were able to put a new game effectively inside of memory. They were able to put new data inside of memory that they can then execute like they would another program. And it's really amazing that they were able to pull this off, because obviously there is no function in Super Mario World that says like play Snake or play Pong. This is something that they had to figure out how to manipulate memory themselves in such a way that would allow them to inject this data into memory. And so that's a really flashy demo of the kinds of things that we'll be talking about today, that kind of method of manipulating memory and inserting this data in such a way that we can execute whatever code we want to. And so that brings us to the topic of shell coding, which here's a quick definition from. Basically, it's going to be a way that we can insert a little piece of machine code into our exploit as the payload, so that when we execute that payload, we're running that machine code, and we can write any kind of machine code we want, and we can write any kind of shell code we want as a result. So for those of you that aren't familiar with the concept of machine code, I think this is something that's talked about a little bit in comporg, but if you haven't taken that class or if you need a refresher, basically the process of compilation is converting that source code that a human can read into that machine code that's just a string of bytes that a human cannot read, but a computer can. So we go from very high level to very low level, and at the end of the day, this machine code, it's just a bunch of bytes. So basically, this revolves around the idea of, like, we can send A's to a program, we can send our name to a program, we can send our age to a program, but what if instead of sending these nice strings, what if we send machine code instead of those things? And so in here, we have the same exact program as before, or a very similar program, I guess I should say, where we have a little character buffer, and then we put data into it. So instead of putting A's in this time, we're putting in these weird bytes, these this complicated byte sequence. And then we talked on Monday a little bit about how we could overwrite a return address and how we could jump to a function. Well, we can't add functions per se, but we can add other code, and then we can jump to that other code. And so once we've injected this code, once we've added that machine code, once we've sent that as input and we've got that in memory somewhere, if we know where in memory it lives, we can just overwrite the return address and point the return address to the start of that machine code instead. We can kind of pretend that it's a function, if you will. So that's kind of a high-level overview of what shellcode is, but I wanted to give you guys a slightly more in-depth explanation of how you can go about writing it for yourself and how you can get a little bit more hands-on experience with it. Basically, any C code can be compiled to machine code. That's what your compiler is doing under the hood. So one common technique when you want to write shellcode is you just write C, and then you use something like NASM or you use GCC even, and you can spit out assembly, or you can even spit out machine code, and you can just dump that and copy and paste that and spit that right into the process that you want to attack. Another really common thing is to use an online assembler, which will allow you to do this at the assembly level instead of the C level. And you can do this by hand too. You can use NASM instead of an online tool. This is just one that I really enjoy and I find very convenient. It's by diffuse.ca, so I'm going to click on that link, and ooh, it's on the wrong screen. Let me drag that in here for you guys. It's going to have this really nice interface where you can select bytes that you want to assemble into, or you can enter assembly, I guess I should say, that which you then compile to machine code, or you can enter raw bytes, which you then decompile, you disassemble. So for example, if we enter like hex 90 and we disassemble that, that's going to give us the instruction, the NOP instruction. We can see similarly if we do EVFE, we disassemble that, that's going to do a jump instruction. So this is a really amazing tool that lets you enter in whatever instructions you want to execute. So maybe we want to move 0 to EAX. You can assemble that. Oh. I don't remember which one of these, what the syntax they expect it to be entered into is, but it's pretty easy to work with once you figure that out. So that allows us to do a lot of really low-level things that we can't necessarily do in C. So for example, we're going to talk about this a little bit later, but oftentimes when you're writing shellcode, you don't want to have null bytes, so you don't want to have that OX00 byte in your shellcode. And the reason for that is because a lot of functions, including gets actually, will terminate input when they see one of those bytes. And so you want to make sure that when you write your shellcode, you don't have a null byte right in the middle of it, because then that function probably won't read your entire shellcode. It will terminate as soon as it sees that null byte. And that's something that's really difficult to do in C, but easy to do by hand. That being said, I've provided some resources here for how you can write your own shellcode. There are other resources, for example, Shellstorm has popped up in the wrong monitor again. Let me drag that over here for you guys. And Shellstorm is going to be a really good resource for finding shellcode that has been written by someone else to do a lot of common tasks. So we can see here we have a lot of different architectures. We have, for example, we have ARM. We saw down below we have 64-bit as well as 32-bit. And then we have Linux. We have a lot of different platforms that we can target as well. Like down here we have Windows exploits. Up here we have Linux exploits. There's a ton of really amazing stuff here. And so, for example, we probably want to be looking for a lot of like ExecV shellcode. We'll be talking a little bit more about what that means in a little bit, but we can find one here. This looks promising. We can just click on that, and it gives us the exact bytes that we need to enter to inject this shellcode. And so shellcoding is really powerful because it lets you do anything that you want. But if you're writing this shellcode by hand, or if you're trying to understand how shellcode works, the concept of a system call, or a syscall as it's often abbreviated, is really, really important. Basically, what a syscall is, it's a really low-level way to interface with the kernel. There are a lot of things that you can't necessarily do in user space. So when you write a random program and you go to execute it, you can't necessarily do those things, but the kernel can, the operating system can. And that system call is basically a way for you to tell the kernel, for you to tell the operating system that you want it to do something. So for example, if you want to do any kind of file system operation, so if you want to read a file or write a file or anything like that, that needs to be done through a system call. If you want to do any kind of memory operation, so like if you're used to malloc or free or anything like that, those are actually wrappers around system calls. Those are utilizing syscalls under the hood. If you want to open a socket, if you want to send data or receive data, that's also done through a system call. A lot of things that we take for granted can only be done with a system call. And so as a result, syscalls are really important for us to understand when we're writing shellcode. And there are a lot of different resources online where you can find fairly complete lists of different system calls and what they do. This particular one is for 64-bit Linux, but there are other ones for 32-bit Linux. It's not as well documented for other operating systems just because they are not open source, and so they're much more prone to change, and you really need to work to get those system call numbers. But we can see there's a ton of system calls, and we can also see that these system calls take arguments, and they do that through these registers that you need to set. So you need to set RAX to the system call number, then you need to set these other registers to the other arguments that you're calling that system call with. And because this is for 64-bit Linux, it is going to be a little bit different than what we're going to be looking at for 32-bit Linux. However, that execv, that sysexecv system call is really, really important for us, because basically what that execv function does is you give it some file and it just runs it. So if you give it, for example, /bin/sh, that's going to run sh, that's going to run a shell, that's going to give us a shell. And ultimately, in a lot of CTFs, that ends up being our end goal, to get a shell. So here's some basic execv shell code that I wanted to show you guys. Now, this is definitely not the most, how should I say, like the most efficient shellcode. This is automatically generated by Pwntools. We talked a little bit before about how it was this, or how Pwntools was this incredibly powerful toolbox, and it had a lot of different functionality. It turns out one of the things that it can do is it can just generate shellcode for you, so you don't need to necessarily go onto shellstorm.org or anything like that. It has a lot of shellcode, like commonly used shellcode, just already set up and ready to go. And this is some of it. However, because it's just generated automatically, because it's just kind of thrown in and included by default. They haven't really done any work to optimize it and to make it take up as few bytes as possible. That being said, I just want to walk you all through it real quick so that you can see what it does and you can kind of see how it works here. I've made a table at the bottom with all of the different registers, as well as another table representing the stack. So when we start off, all of these registers are set to unknown values, except we know that ESP points to the top of that stack. Then when we start executing this code, it's going to push all of these random looking bytes. But if we actually go online and we find a hex converter, or if we just plug this into Python and we have Python convert it for us, we can see that this actually corresponds to the string /bin //sh, and then it will be null terminated because it isn't taking up the full 8 bytes. So after these 3 instructions are executed, ESP here will point to the string /bin /sh. Then we're going to essentially move ESP into the EBX register. So EBX will now point to the string /bin /sh. And then this is kind of one of the funky things that Pwntools is doing that makes it a little bit harder to read. But basically it's going to push this string, and then it's going to XOR that series of bytes with another series of bytes. And that's a really weird and convoluted way of doing it, but at the end of the day, what that's going to end up doing is it's going to essentially push another SH string. Then we're going to XOR ECX with itself. For those of you that are familiar with bitwise arithmetic, you'll know that XORing with itself, XORing something with itself, always gives you 0. And so when we XOR and we push, we're going to be pushing 0 onto the stack. So effectively a null terminator. After that, we're going to be pushing the number 4, popping that into ECX. So ECX is now going to be equal to 4. And then we're going to add ECX. We're going to add 4 to ESP here. And at the end of all of that, ECX should be pointing, so that means that the thing at the top of the stack here is going to be pointing to 4 bytes above it. ECX will be pointing to that. So essentially, ECX is pointing to another pointer of that SH string. Finally, we're going to XOR EDX with itself, so that's going to give us a 0 again, as we discovered earlier. And then we're going to push OXB and pop it into EAX. So if we remember from earlier, EAX is going to be the syscall number. So we know that OXB will be the syscall number for ExecV, and then we're going to feed it in the string /bin /sh as an argument. And then that sh, if I remember correctly, that register is going to be for like an argument or for an environment pointer. And then finally, we're going to call int80, which is the 32-bit way of essentially making a system call. That interrupt 80 is effectively a way for us to interact with the kernel. So that's a really quick overview of what shellcoding is and how it works. I want to talk a little bit about some of the constraints really quickly, and then I think we'll be calling it a day pretty soon because we have a CTF happening right now, and we'll be spending the rest of the evening working on that. So if you're watching this live right now, if you want to join us for Hack the Vote after we finish, that will be another really good way to get some hands-on experience with shellcoding and other security topics. So I alluded to this earlier, but null bytes are probably one of the biggest constraints that we see for shellcode, because when we call something like gets or fgets or anything in that family, it's going to terminate on a null byte. And so if it sees that OX00, it's just going to stop reading any more input. And if that happens during the middle of our shellcode, we won't get all of our code injected and we won't be able to execute anything we want. And so because of that, we have a lot of really interesting ways of encoding instructions. So a couple of minutes ago, I was talking about how a lot of people like to either write shellcode by hand or compile and then tweak it by hand. The reason for that is because we can encode these instructions differently. So a compiler by default might do something like a move RDI 0. And that's great, that's going to get that value into the register RDI. But A, it's going to take up a lot of bytes. And B, that's going to be including a lot of null bytes. And that's going to be really bad for our shellcode. So oftentimes you'll see that Zoring trick that we talked about before being used instead of a move instruction. And sometimes you'll see the same exact thing instead of, for example, like moving a value into a register. We might be pushing a value and then popping it into a register. So if we look at that shellcode that Pwntools generates for us, we can see it does this weird thing where it pushes OXB and then it pops it instead of just using a move instruction. So that seems like it would take a lot longer because it's a move instruction, or because it's 2 instructions instead of 1. But for our purpose, it's actually a much better option. So yeah, null bytes are definitely the most common thing that we're trying to constrain, we're trying to get rid of in our shellcode. But sometimes we see other really interesting challenges as well. So for example, oftentimes in CTFs, we'll have challenges that require us to have alphanumeric shellcode, so it can only be printable ASCII. And as you can imagine, that makes things a lot more difficult because you need to be thinking about what instructions correspond to what bytes, and what bytes correspond to what ASCII values. So constraining shellcode is a really, really common thing that we run into. That being said, I think that's it for today. We will be playing Hack the Vote as soon as this meeting ends, so feel free to join us for that, and I will see you